Sometimes the best way to figure out what examiners are really looking for is to think like one. So today, that's exactly what we're going to do. We're going to break down an official AQA physics exam question, and we'll use the official mark scheme to see what separates a good answer from a truly top marks answer. Okay, let's get right into it. Here's our roadmap for today. We're taking on question 2 from the AQA June 2022 higher tier physics paper. We're going to go through every single part, look at the exact answers from the mark scheme, and then, at the end, we'll zoom out and see what key skills this question was really testing. First things first, let's set the stage. You have to know the context of where a question comes from, because that's really the first step to cracking it.
So, we're locked in on question 2. Now, this isn't just a simple one-and-done question. Oh no, it's a multi-part beast with a total of 10 marks, and it's built to test a whole mix of things: your practical skills, how you handle data, and your fundamental understanding of the scientific process.
All right, first up is the big one. This part is worth a whopping 6 marks, and it asks you to describe an entire experimental method completely from scratch.
So this is what's called a level of response question, and it's a classic. What that means is the examiner isn't just ticking off keywords from a list. They are actually reading your answer to see if it's logical, if it's clear. You have to tell a coherent story about your experiment from beginning to end. Just throwing down a jumbled list of correct steps, well, that's just not going to get you those top marks. And that's why understanding the mark scheme is everything. It gives you what's called indicative content. Now, this isn't a perfect script you have to memorize. Think of it more like a guide, the essential ingredients an examiner is looking for. For this question, they'll credit one of 2 perfectly valid methods for finding the rock's volume. So here's the first method they'll accept, and it's probably the most direct way to do it. You start simple. Measure the mass on a balance. Next, you find the volume. You do this by putting some water in a measuring cylinder, writing down that initial volume, carefully sliding the rock in, and then measuring the new final volume. The difference between those 2 numbers, that's your rock's volume. Simple, logical, and gets you the marks.
Now, here's the alternative approach, using what's called a displacement can, or a eureka can. This thing is brilliant for objects that are weirdly shaped or a bit too big for a measuring cylinder. You just fill the can right up to the little spout, gently place the rock inside, and then you collect all the water that spills out. The volume of that collected water is exactly the same as the volume of the rock.
Now listen up, because this is absolutely crucial. Whichever method you picked for finding the volume, whether it was the measuring cylinder or the displacement can, you have to finish your answer by stating how you're going to use that data. You must explicitly say that you'll use the mass and the volume you found to calculate the density using the correct formula. Don't leave it out. All right, so from describing a method, the question now pivots. Part 2 is all about testing your ability to work with a bit of experimental uncertainty. Let's see how it works.
Here is the question exactly as it appeared on the paper. You're told the student's result is 2.55 plus or minus 0.10 grams per centimeter cubed. All it asks is for you to state the maximum and minimum possible values for the density.
And the mark scheme here is super direct. 1 mark, and you have to get both of these values exactly right. It's a really straightforward calculation. For the maximum possible density, you just add the uncertainty, so 2.55 plus 0.10 is 2.65. For the minimum, you do the opposite and subtract it, which gives you 2.45. Simple as that. Okay, on to part 3. This is where we have to put that range we just calculated to work. This is all about comparing an experimental result with a set of known scientific values. So the task here is to look at Table 1. It lists the densities of a bunch of different types of rock. Your job is to play detective and figure out which of those rocks the student might actually have, based on their measurement. First, let's just take a look at the data we're given. And the key thing to notice is that each rock type also has its own uncertainty range. So the trick to solving this is to figure out the full density range for each rock, and then see which of those ranges overlaps with the student's measured range, which we know is between 2.45 and 2.65. So the only correct answer, according to the mark scheme, is chalk or flint. And let's quickly see why. If you look at chalk, its range is 2.20 up to 2.50. And for flint, its range is 2.50 up to 2.70. You can see that both of those ranges have some overlap with the student's measured range of 2.45 to 2.65. So it could be either one. Let's move on to the final part of the question. This 2-mark question is all about good experimental practice. It gets to the heart of why scientists do what they do.
So the question points out, hey, the student only took one set of measurements. And then it asks you to explain why taking measurements more than once could actually improve the accuracy of the result. Why bother repeating?
Well, the mark scheme accepts two key reasons. The first and most common one is that repeating measurements allows you to calculate a mean, an average. And this is so important because it helps to reduce the effect of random errors, those little unpredictable wobbles in your measurements. The alternative answer, which is also perfectly valid, is that repeating your measurements helps you spot any anomalies. Any results that are clear outliers and just don't look right. You can then remove them before you calculate your final value.
So we've picked this question apart, piece by piece, and looked at the official answers. But let's zoom out for a second. What's the big picture? What fundamental skills was this one question about density really testing?
This one question covers such a huge range of essential scientific skills. I mean, it's not just about knowing a formula. It's about planning, it's about analyzing, it's about comparing, and it's about evaluating. These are the skills that are fundamental to all scientific work, whether you're in a school classroom or a professional research lab.
And that's our deep dive into question 2. If there's one thing to take away, it's this: understanding the process. How to do an experiment the right way, how to handle your data, how to think critically about your results, that's just as important as memorizing facts. Master that, and you're really starting to think like a scientist. Thanks for joining this explainer.